Hello students, welcome to the second module, Differential Calculus 2. As you are already familiar with the concept of sequence and series, in this video we learn a special kind of series introduced by the mathematician Taylor. Let us start with the theorem proposed by him, Taylor's theorem, which states that say suppose the function f of x and its n-1th derivatives are continuous in the closed interval a, a plus h, and its nth derivatives exist in the open interval a, a plus h, then the expansion of f of a plus h is given by f of a plus h into f dash of a plus h square by 2 factorial into f double dash of a, and so on. The last term is h to the power n divided by n factorial into nth derivative of f at a plus theta h, where theta is at least one member in the interval 0, 1. If a is equal to 0, then the Taylor's theorems is called Maclaurin's theorems. Using the above theorem, the Taylor expansion of the function f of x about the point x is equal to a is given by f of x is equal to f of a plus x minus a into f dash of a plus x minus a whole square divided by 2 factorial into f double dash of a plus x minus a whole cube divided by 3 factorial into f triple dash of a plus x minus a whole to the power 4 by 4 factorial into fourth derivative of f at a, and so on. Or y is equal to y of a plus x minus a into y1 of a plus x minus a whole square by 2 factorial into y2 of a plus x minus a whole cube by 3 factorial into y3 of a plus x minus a whole to the power 4 by 4 factorial into y4 of a, and so on. When a is equal to 0, the series is called Maclaurin series. So that the Maclaurin series expansion of the function f of x is given by f of x is equal to f of 0 plus x into f dash of 0 plus x square by 2 factorial into f double dash of 0 plus x cube by 3 factorial into f triple dash of 0 plus x to the power 4 by 4 factorial into fourth derivative of f at 0, and so on. Or y is equal to y of 0 plus x into y1 of 0 plus x square by 2 factorial into y2 of 0 plus x cube by 3 factorial into y3 of 0 plus x to the power 4 by 4 factorial into y4 of 0, and so on. Just remember this series expansion as we are going to use it in problems. First problem, expand y is equal to sin x in powers of x minus pi by 2. Since we have to expand y is equal to sin x as a power of x minus pi by 2, which is of the form x minus a, wherever a is non-zero. This results in Taylor series expansion about a is equal to pi by 2. Therefore, by Taylor series, y is equal to y of a plus x minus a into y1 of a plus x minus a whole square by 2 factorial into y2 of a plus x minus a whole cube by 3 factorial into y3 of a, and so on. Since here the unknowns are y of a, y1 of a, y2 of a, y3 of a, y4 of a, and so on, right? First we have to find these unknowns. Since you know y is equal to sin x. From that you can get y of a, that is y of pi by 2, that is sin pi by 2, which is equal to 1. Therefore y of pi by 2 is equal to 1. To get y1, differentiate y. So derivative of sin x is cos x. Therefore y1 of pi by 2 is equal to 0, because cos pi by 2 is 0. Now y2, derivative of cos x is minus sin x. Therefore y2 of pi by 2 is equal to minus 1. y3 is equal to minus of derivative of sin x, that is minus cos x. Therefore y3 of pi by 2 is equal to 0. y4, minus of derivative of cos x is minus sin x. Therefore y4 is sin x, which implies y4 of pi by 2 is equal to 1. Now substitute y1, y2, y3 and y4 at pi by 2 in the Taylor series, so that we will get the series expansion of sin x about the point pi by 2 as sin x is equal to 1 minus x minus pi by 2 whole square by 2 factorial plus x minus pi by 2 whole to the power 4 divided by 4 factorial, and so on. Next problem. Obtain the Taylor series expansion of log x about the point x is equal to 1 up to the term containing 4th degree, and hence obtain log 1.1. Taylor series expansion about x is equal to a is given by y is equal to y of a plus x minus a into y1 of a plus x minus a whole square by 2 factorial into y2 of a plus x minus a whole cube by 3 factorial into y3 of a, and so on. Clearly a value is 1. Now get the unknowns. Since y is equal to log x, which implies y of 1 is equal to log 1, which is 0. y1 is derivative of log x, that is 1 by x, which implies y1 of 1 is equal to 1. y2 is equal to derivative of 1 by x, that is minus 1 by x square. Therefore y2 of 1 is equal to minus 1. y3 is derivative of minus 1 by x square, which is 2 by x cube, which implies y3 of 1 is equal to 2. y4 is derivative of 2 by x cube, which is minus 6 by x to the power 4. Therefore y4 of 1 is minus 6. Since Taylor series up to the 4th degree term with a is equal to 1 is y is equal to y of 1 plus x minus 1 into y1 of 1 plus x minus 1 whole square by 2 factorial into y2 of 1 plus x minus 1 whole cube by 3 factorial into y3 of 1, and so on. But y is log x. Therefore log x is equal to y of 1 is 0. Substitute 0 here, plus x minus 1 into y1 of 1. y1 of 1 is 1. Substitute 1, plus x minus 1 whole square by 2 factorial into y2 of 1. y2 of 1 value is minus 1, plus x minus 1 whole cube by 3 factorial into y3 of 1. y3 of 1 value is 2, plus x minus 1 whole to the power 4 by 4 factorial into y4 of 1. y4 of 1 value is minus 6. Now by simplification, you will get log x is equal to x minus 1 minus x minus 1 whole square divided by 2 plus x minus 1 whole cube by 3 minus x minus 1 whole to the power 4 by 4. To get log of 1.1, substitute x is equal to 1.1 in the series expansion of log x, so that we will get log of 1.1 which is equal to 0.0953. Next is problems on Maclaurin series. First problem, find Maclaurin series of y is equal to tan x. Since Maclaurin series is given by y is equal to y of 0 plus x into y1 of 0 plus x square by 2 factorial into y2 of 0 plus x cube by 3 factorial into y3 of 0 and so on. Y of 0, y1 of 0, y2 of 0, y3 of 0 and so on are the unknowns to find. Since y is equal to tan x implies y of 0 is equal to tan 0, which is 0. To get y1, differentiate tan x with respect to x, and derivative of tan x is secant square x. Therefore, y1 is equal to secant square x. But to get the higher order derivative, let me rewrite secant square x as 1 plus tan square x, that is 1 plus y square. Therefore, y1 of 0 is equal to 1 plus 0 square, which is equal to 1. Next is y2. Derivative of 1 is 0 and derivative of y square is 2 into y1, that is by chain rule. Therefore, y2 is 2 into y1, which implies y2 of 0 is equal to 2 into 0 into 1, which is equal to 0. y3 is 2 into, apply the product rule, that is y into derivative of y1 is y2 plus y1 into derivative of y is y1. Therefore, y3 is equal to 2 into y2 plus 2 into y1 square, which implies y3 of 0 is equal to 2. y4 is equal to 2 into y into derivative of y2 is y3 plus y2 into derivative of y is y1 plus derivative of y1 square is 2 into y1 into y2. Therefore, y4 is equal to 2 into y3 plus 6 times y1 into y2. Therefore, y4 of 0 is equal to 0. y5 is equal to, take 2 outside, y into derivative of y3 is y4 plus y3 into derivative of y is y1 plus 3 times y1 into derivative of y2 is y3 plus y2 into derivative of y1 is y2. Therefore, y5 is equal to 2 times y into y4 plus 8 times y1 into y3 plus 6 times y2 square, which implies y5 of 0 is equal to 16. Now by substituting the unknowns, you will get tan x is equal to x plus x cube by 3 plus 2 into x to the power 5 by 15 and so on. Next problem, find Maclaurin series of e power x. E power x is one of the simplest functions since its higher order derivatives are itself, so that we can easily observe y1, y2, y3, y4 is e power x, so that the corresponding values of the derivatives at x is equal to 0 is 1. Substituting it in the above Maclaurin series, we get e power x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Next problem, find Maclaurin series of cos x. Maclaurin series is given by y is equal to y of 0 plus x into y1 of 0 plus x square by 2 factorial into y2 of 0 and so on. Y is cos x implies y of 0 is 1. y1 is differentiate y with respect to x and derivative of cos x is minus sin x. Therefore, y1 is equal to minus sin x, which implies y1 of 0 is 0. y2 is minus into derivative of sin x is cos x. Therefore, y2 is minus cos x, which implies y2 of 0 is minus 1. y3 is equal to derivative of cos x is minus sin x, but 1 minus sin is already outside, so it becomes plus sin x. Therefore, y3 is sin x, which implies y3 of 0 is 0. Similarly, y4 is derivative of sin x is cos x. So y4 is cos x, which implies y4 of 0 is 1. By substituting y of 0, y1 of 0, y2 of 0, y3 of 0 and y4 of 0 in the above Maclaurin series, we will get cos x is equal to 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial and so on. Next problem. Find the Maclaurin series of cos hyperbolic x and sin hyperbolic x. As you are already familiar that cos hyperbolic x can be expressed as e power x plus e power minus x divided by 2. And we know that the Maclaurin series expansion of e power x is 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. Students, just make a note of it as exponential is a standard function, hence you have to remember the series expansion of it. Similarly, series expansion of e power minus x can be obtained by replacing x by minus x in the above expansion. Adding the series expansion of the two function term by term and dividing it by 2, you will get cos hyperbolic x equal to 1 plus x square by 2 factorial plus x to the power 4 by 4 factorial plus x to the power 6 by 6 factorial and so on. In the same way, we can also obtain the series expansion of sin hyperbolic x, which is equal to x plus x cube by 3 factorial plus x to the power 5 by 5 factorial and so on. Find Maclaurin series of y is equal to log of 1 plus x. Since Maclaurin series is given by y is equal to y of 0 plus x into y1 of 0 plus x square by 2 factorial into y2 of 0 and so on. Since y is equal to log of 1 plus x implies y of 0 is equal to log 1, which is equal to 0. To get y1, differentiate log of 1 plus x with respect to x, and derivative of log of 1 plus x is 1 divided by 1 plus x. Therefore, y1 is equal to 1 divided by 1 plus x, which implies y1 of 0 is equal to 1. To get higher order derivative, just remember the formula d by dx of 1 by x power n is minus n divided by x to the power n plus 1. Therefore, y2 is equal to minus 1 divided by 1 plus x whole square, which implies y2 of 0 is equal to minus 1. y3 is minus of minus 2 divided by 1 plus x whole to the power 2 plus 1, which is equal to 2 divided by 1 plus x whole cube. Therefore, y3 of 0 is equal to 2. And y4 is 2 times minus 3 divided by 1 plus x whole to the power 4, which is equal to minus 6 divided by 1 plus x whole to the power 4. Therefore, y4 of 0 is equal to minus 6. After substitution, log of 1 plus x is x minus x square by 2 factorial plus x cube by 3 minus x to the power 4 by 4 and so on. Next problem. Find Maclaurin series of log of secant x. Since y is equal to log of secant x implies y of 0 is equal to log secant 0, that is equal to log 1, which is equal to 0. To get y1, differentiate log of secant x with respect to x, and derivative of log of secant x is 1 by secant x into secant x into tan x. Therefore, y1 is equal to tan x, which implies y of 0 is equal to tan 0, which is equal to 0. y2 is derivative of tan x is secant square x, and secant square x is 1 plus tan square x. Therefore, I can write y2 as 1 plus y1 square, which implies y2 of 0 is equal to 1. y3 is equal to derivative of 1 is 0 and derivative of y1 square is 2y1 into y2. Therefore, y3 is equal to 2y1 into y2, which implies y3 of 0 is equal to 0. y4 is 2 into y1 into y3 plus 2 into y2 square, which implies y4 of 0 is equal to 2. y5 is 2 into y1 into y4 plus 6 times y2 y3, which implies y5 of 0 is 0, and y6 is 2 times y1 into y5 plus 8 times y2 into y4 plus 6 times y3 square, which implies y6 of 0 is 16. Therefore, log of secant x is x square by 2 plus x to the power 4 by 12 plus x to the power 6 by 45 and so on. Find Maclaurin series of y is equal to tan inverse of x. Y is equal to tan inverse of x implies y of 0 is equal to tan inverse of 0, which is equal to 0. To get y1, differentiate y is equal to tan inverse of x with respect to x, and derivative of tan inverse of x is 1 by 1 plus x square. Therefore, y1 is equal to 1 by 1 plus x square. But to get higher order derivatives, I can rewrite it as y1 into 1 plus x square is equal to 1, and y1 of 0 is equal to 1. Now differentiate 1 plus x square into y1 is equal to 1 with respect to x. By product rule, 1 plus x square into derivative of y1 is y2 plus y1 into derivative of 1 plus x square is 2x, which is equal to 0, which implies y2 of 0 is equal to 0. To get y3, 1 plus x square into derivative of y2 is y3 plus y2 into derivative of 1 plus x square is 2x plus 2 times x into derivative of y1 is y2 plus y1 into derivative of x is 1, which is equal to 0. That is 1 plus x square into y3 plus 4 times x into y2 plus 2 times y1 is equal to 0, which implies y3 of 0 is equal to minus 2. Next, 1 plus x square into derivative of y3 is y4 plus y3 into derivative of 1 plus x square is 2x plus 4 times x into derivative of y2 is y3 plus y2 into derivative of x is 1 plus 2 times derivative of y1 is y2, which is equal to 0, or 1 plus x square into y4 plus 6 times x into y3 plus 6 times y2 is equal to 0, which implies y4 of 0 is equal to 0. Similarly, to get y5, differentiate the above expression so that you will get 1 plus x square into y5 plus 8 times x into y4 plus 12 times y3 is equal to 0, which implies y5 of 0 is equal to 24. Thus, after substituting the unknowns, you will get tan inverse of x is equal to x minus x cubed by 3 plus x to the power 5 by 5 and so on. Next problem. Find Maclaurin series of root of 1 plus sine 2x. Since Maclaurin series is given by y is equal to y of 0 plus x into y1 of 0 plus x square by 2 factorial into y2 of 0 and so on. To get the unknowns, first make the given function simpler so that you can easily get the higher order derivatives. Since y is equal to root of 1 plus sine 2x, but I can write 1 as sine square x plus cos square x and sine 2x as 2 sine x into cos x. So that root of 1 plus sine 2x becomes sine square x plus cos square x plus 2 into sine x into cos x, but which is of the form a plus b whole square. So I can write root of 1 plus sine 2x as root of sine x plus cos x whole square, which is equal to sine x plus cos x. Therefore, y is equal to sine x plus cos x, which implies y of 0 is equal to 1. To get y1, differentiate y is equal to sin x plus cos x with respect to x, and derivative of sin x is cos x and derivative of cos x is minus sin x. Therefore, y1 is equal to cos x minus sin x, which implies y1 of 0 is equal to 1. y2 is equal to minus sin x minus cos x, implies y2 of 0 is equal to minus 1. Similarly, y3 is equal to minus cos x plus sin x, which implies y3 of 0 is minus 1, and y4 is equal to sin x plus cos x, which implies y4 of 0 is equal to 1. Therefore, root of 1 plus sine 2x is equal to 1 plus x minus x square by 2 factorial minus x cube by 3 factorial plus x to the power 4 by 4 factorial and so on. Next problem. Find Maclaurin series of e power sin x. Since y is equal to e power sin x implies y of 0 is equal to e power sin 0. Sin 0 is 0, that is e power 0, which is equal to 1. y1 is equal to derivative of e power sin x is e power sin x into derivative of sin x is cos x, that is y1 is equal to e power sin x into cos x, or I can write it as y into cos x. Therefore, y1 is equal to y into cos x implies y1 of 0 is equal to 1. y2 is equal to y into derivative of cos x is minus sin x plus cos x into derivative of y is y1. That is, y2 is equal to minus y into sin x plus cos x into y1. Therefore, y2 of 0 is equal to 1. y3 is equal to minus of y into derivative of sin x is cos x plus sin x into derivative of y is y1 plus cos x into derivative of y1 is y2 plus y1 into derivative of cos x is minus sin x, or y3 is equal to minus y cos x minus 2 times y1 into sin x plus y2 into cos x, which implies y3 of 0 is equal to 0. Similarly, y4 is equal to y into sin x minus 3 times y1 into cos x minus 3 times y2 into sin x plus y3 into cos x, which implies y4 of 0 is equal to minus 3. Therefore, e power sin x is equal to 1 plus x square by 2 minus x to the power 4 by 8 and so on. Last problem. Find Maclaurin series of e power x into cos x. Y is equal to e power x into cos x implies y of 0 is equal to 1. Y1 is equal to e power x into derivative of cos x is minus sin x plus cos x into derivative of e power x is e power x. But cos x into e power x is nothing but y. Therefore, y1 is equal to y minus e power x into sin x, which implies y1 of 0 is equal to 1. Y2 is equal to derivative of y is y1 and derivative of e power x into sin x is e power x into cos x plus sin x into e power x. Therefore, y2 is equal to y1 minus y minus e power x into sin x, which implies y2 of 0 is equal to 0. Y3 is equal to y2 minus y1 minus y minus e power x into sin x, which implies y3 of 0 is equal to minus 2, and y4 is equal to y3 minus y2 minus y1 minus y minus e power x into sin x, which implies y4 of 0 is equal to minus 4. Therefore, e power x into cos x is equal to 1 plus x minus x cube by 3 minus x to the power 4 by 6 and so on.